Workout 5.3, let's talk about it. Number 1, internet sites often vanish or move so that references to them can't be followed. In fact, 13% of internet sites referenced in major scientific journals are lost within 2 years after publication. If we randomly select 7 internet references from scientific journals, what is the probability that at least one of them does not work, therefore is lost, work 2 years later? So the probability of being lost is 0.13. And we are being asked to find the probability that at least one of 7 is lost or doesn't work. That would be a tedious task to figure out. So we're going to use our at least one rule. We're going to do 1 minus the probability that none are lost. None of the 7 are going to be lost. All right? So none of the 7 are lost. But I only have the probability that they're lost. Is there any way to find the probability that's not lost? Yes. So what is the probability of not being lost for a single internet site? 0.87. How'd you get 0.87?
Just subtract 0.87.
Yeah, let's go. So this is the probability that one of them is not lost. But I need to know the probability that none of the 7 are lost. So this would be 1 minus the probability that none are lost. So the first one is not lost is 0.87. Probably the second one is not lost, 0.87. Third, 0.87. Fourth, you get the idea. So 0.87 7 times. 0.87 to the 7th power. Once I solve that little calculation there, I got my answer. What is 1 minus 0.87 to the 7th power?
0.62. Wait, no.
Yeah. Yeah.
Yeah.
0.6227. So there is a 62.27% chance that at least one of the 7 is going to be lost. What questions do you guys have about the at least one rule and number 1? Aight, let's look at number 2. Number 2 makes me angry. All right, let's look at number 2. Number 2 says, suppose events E and F are mutually exclusive. Ladies and gentlemen, what does it mean for things to be mutually exclusive?
They can't happen at the same time.
They cannot happen at the same time. Find the value of the probability of E and F happening at the same time. 0. This is a big fat 0 right there. That's all it is. Why we're missing that, I'm not sure. But the probability of 2 mutually exclusive events happening at the same time is 0. All right. Now, it says what's the probability of E or F? Now, when you have mutually exclusive events, you can just add their probabilities. And you don't have to worry about an overlap because there is no overlap. So these 2 events are mutually exclusive. So I can just take the probability of E and add the probability of F. And I ain't got to worry about no overlap because there is no overlap. So I just take 0.14 and add 0.76. And this is my probability of E or F, 0.9. So, moral of the story. Mutually exclusive events cannot happen at the same time. The probability of mutually exclusive events having an and is 0. When you have mutually exclusive events, you can just add their probabilities to get the or probability. What is the probability of mutually exclusive events having an overlap? Oh, dang. What is the probability of mutually exclusive events having an overlap? 0. So the probability of 2 mutually exclusive events having an and is 0. What can you do with mutually exclusive events? Mathematically speaking, you can add them. And when you add them, you get the or probability. Got it? Let's see if you got it. Let's do another problem. Number 3. Suppose that these two events, I know yours says A and B, but it should have said D and G. Suppose that these two events, D and G, the probability of D is 0.36, probability of G is 0.36. The probability of D or G is 0.72. Are these mutually exclusive? Let's find out. If they are mutually exclusive, what can I do with them? Add their probabilities to get the OR probability. So let's just see. If I add 0.36 to 0.36, what do I get? I get the OR probability. I didn't have to subtract an overlap because apparently there is no overlap. Are these two events mutually exclusive? Yes, they are mutually exclusive. Isn't that fun? I have a question for y'all. What's the probability of two events happening at the same time if they're mutually exclusive? 0. What can I do with mutually exclusive events, mathematically speaking? I can add them, and what will that give me? The OR probability. You got it. All right, let's look at number 4. Who's having fun? Me too. Suppose events R and L are independent. Now, time out. Does independence have anything to do with mutually exclusive? Nope. Those are two separate ideas that have to be checked separately. However, this tells me that the probability of R and L is 0.21. Does that tell me anything about mutually exclusivity? Yes. It sure does. If the probability of them overlapping is anything other than 0, they're not mutually exclusive. So are these guys mutually exclusive? No. They happen at the same time 21% of the time. They are not mutually exclusive. Not even a little. All right, cool. The probability of R is 0.7. What is the value of the probability of L? So I want to tell you guys a little bit about independence. What, first of all, does it mean for two things to be independent? Yeah, they're not related. They're not influencing each other in any way. So these two things are independent. They're not influencing each other in any way. Whatever the probability of the second event is, has no bearance on the first probability. Okay. When two things are independent, you can multiply them without any worry. If two things are independent, you can multiply them and get the AND probability. Two things are independent, you can multiply them and get the AND probability. So, the probability of R and L is the probability of R times the probability of L if they are independent. If two things are independent, I can multiply their probabilities and get the AND probability. So let's see what we are missing. So, since it tells me in the problem that they're independent, I can plug in 0.21 equals 0.7 times this unknown probability. Well, dang it, it looks like we need a little bit of algebra. What do we do here to fix this or to find this unknown? We're going to divide both sides by 0.7. Divide by 0.7. What is the probability of L? 0.3. Since they were independent, what was I able to do with them? Divide. Okay, yes, which is also similar to multiply. And that gave us the AND probability. All right, what is the probability of R or L? Okay, so this asks for an OR. Were these mutually exclusive? They were not, because they overlapped 21% of the time. So remember, for that, R or L, when they're not mutually exclusive, I can still add them, but I do need to handle the overlap and subtract off that overlap. Again, this formula is on your formula chart. The only kind of tweak on this formula is when they're mutually exclusive, the probability of the overlap is 0. So this is your formula for the OR. Probability of R was 0.7. Probability of L we solved was 0.3. We can subtract the overlap of 21, and this will give us 0.79. The probability of R or L occurring is 0.79. I have a question for you.
What is the question?
What does mutually exclusive mean? Cannot happen at the same time. What's the probability of A and B when they are mutually exclusive? 0. What can you do with mutually exclusive events? Add them. And what does that give you? The OR probability. Independence. What does that mean? They're not related. They're not influencing each other in any way. What can I do with independent events? Multiply them to get and. The and probability. Cool?
Yeah.
Okay. Is this starting to kind of sink in a little?
Yes.
All right, good. I'm so glad. Children sending letter to Santa. Don't you guys love Santa?
No.
Santa's the best. So look, children can send letters to Santa by email, snail mail, or filling out a Google Doc. We're all technological these days. Children who send a letter to Santa sometimes don't get a response, you guys. Suppose a child who wrote a letter to Santa is selected at random. Consider these two events. E is that they sent an email to Santa. N is that they did not get a response back. The probability of an email is 0.6. The probability of not getting a response is 0.14. And the probability of E and N is 0.09. Time out. Are these mutually exclusive? No, why not? The and is not 0, immediately makes this not mutually exclusive. Okay, perfect. Are these events independent? If they were independent, what could I do with their probabilities? Multiply them to get the and probability. So let's just see if that happens. Let's see. If I take the probability of E and I multiply by the probability of N, do I get the probability of E and N, which would be true if independent? So let's just check. 0.6 times 0.14. Does that equal 0.09? What is 0.6 times 0.14? 0.084. Does that equal 0.09? No. So are these independent? These are not independent, you guys, because these do not equal each other. What that means is that if I know that a kid sent an email, I can better predict whether or not they got a response, and vice versa. That means that these are influencing each other in some way. Do I know what way? Not really, but I know that they are influencing each other in some way. Probability of E or N. Yes. You can also use, yes, okay, thank you for notating that. Yes, so that's one way to check it. Let me show you guys another way to check this. There is the other way to check independence, which was, I showed you guys how to prove independence. So this is another way. You can do the probability of E given N has to equal the probability of E, and vice versa with N and E. So we can check this. So the probability of E given N would be the probability of E and N divided by the probability of the given. That would have to equal the probability of E. So the probability of E and N was told to us as 0.09 divided by 0.14. That would have to equal 0.6. When you do the math there, you will quickly find that they do not equal each other. So again, not independent. So yes, either way works. Cool?
Yeah.
Cool. All right. E or N. Guys, it's asking me for or. Can I just add their probabilities and not worry about anything else?
No.
Why not? They're not mutually exclusive. Remember, there's an and probability which means that they're not mutually exclusive. So I am going to have to worry about the overlap. So the probability of E or N is the probability of E plus the probability of N minus the overlap of E and N. So 0.6 plus 0.14 minus 0.09 is your answer. 0.6 plus 0.14 minus 0.09, I believe, is 0.65. Cool? Cool. What is the probability of A and B if they are mutually exclusive?
0.
Very good. What can I do with mutually exclusive events? Add them to get what? Or. What can I do with independent events? Multiply to get the and probability. You got it. You got it. All right, cool, cool. Moving along. Number 6. Okay, number 6. The table below gives the counts in thousands of earned degrees in the United States in a recent year, classified by highest level of education and by gender of the degree recipient. Part A. There's no math involved here.
Yay.
Are the events professional degree and female mutually exclusive? What we're asking here is, can professional degree overlap with being a female? Can females have a professional degree?
Yes.
Yeah, in fact, 30,000, because these are all in thousands, 30,000 of them did. So are these mutually exclusive? No, not even a little. All right, so these are no, because professional degree and female can and did overlap. They happen at the same time. Now, you want to know what is mutually exclusive here? Being a female and being a male. Those are mutually exclusive. I can't be both of those at the same time. You know what else is mutually exclusive? Because this is basically talking about highest level of degree. Having a bachelor's and having a professional degree. I can't be in both of those columns at the same time because I'm talking about the highest level, not both. So anytime you're trying to find mutually exclusive events in a table, any of the columns would be mutually exclusive, and any of the rows with each other are mutually exclusive because you're in one category, not multiple. All right, is master's degree and male independent? To find out, we need to find out, does the probability of masters, given that they're male, does that equal the probability of being a male? Basically, if this, I'm sorry, not the male, the probability of a master's, my bad. Basically here, if this is true, if the probability of masters given that they're male equals the probability of just a master's degree anyway, that means that male has no bearing on whether or not they have a master's degree. But if these don't equal each other, then the male is influencing the master's degree in some way. So let's use our table to find this out. Given that they are male, so I'm in that row, what's the probability that they have a master's degree? 171 over 770. Now, does that equal the probability in this population of having a master's degree? So if I look at everybody again, the probability of having a master's degree is 365 out of the total of 1626. Do these two equal each other? I cannot look at those fractions and tell you if they do or not. But if you throw those in a calculator, you should see that 171 over 770 is 0.221, I believe.
Yeah.
And the other one, the master's degree, is 0.224. You guys, they're close. But close is not good enough for independence. They have to truly be different, or they have to truly be exactly the same. So this is not close enough for independence. These are not independent. Now, the fact that they're close does tell me this. I'm not going to be able to very easily use the first event to predict the second, but there is going to be some sort of an association here. Okay, it's not going to be very clear, it's not going to be very helpful, but there's going to be something going on there. Alrighty, part C. Part C says, what is the probability that the selected person is female given that they have a doctorate degree? I want to know the probability of female given they're in the doctorate degree. It's literally just 16 over 42, whatever 16 over 42 is. Part D. Part D is also very similar to that one. What is the probability that the selected person has a bachelor's degree given that they are male? So given that they're male, what's the probability of a bachelor's degree? So part D would be 529 over 770. That's just the conditional probability of having a bachelor's degree given that we're in this male column. Cool beans? Okay. All right, let's look at number 7. Suppose a person was having 2 surgeries performed at the same time by different operating teams. Maybe they're having a facelift and a toenail extracted. I don't know. Whatever. So assume, unrealistically, that these are independent surgeries. Okay, it just told you that there's independence here. So you can probably bet that you're going to have to multiply something because you were told that they were independent. If the chances of success for surgery A are 85%, so the probability that A is good is 0.85, and the chances for success for surgery B are 90, what is the probability that both will fail? Oh, wow. If I multiply these two, what would I have? If I multiplied these two values, what would I actually be finding?
The opposite of what you want.
I would be finding the probability that they both succeed, okay? So what I need to do is I need to find the probability that each of them fails. So what is the probability that A fails? 0.15. It's the complement of it succeeding. And what's the probability that B fails? 0.1. Now I know the probability of each of them failing independently, and now I can multiply their failure rates in order to find out what the probability is that they both fail. So 0.15 times 0.1 is 0.015. That would be the probability that they both fail. So there's only a 1.5% chance that your facelift and your toenail extraction is going to fail together. It's good news. Good news. All right, let's talk about twins. Anybody a twin in here?
Yes.
You are?
Yes.
Nice.
Twins actually, I think, in your 6th period, so that's kind of cool.
Your twin is in my 6th period?
Yeah.
No way.
Yes.
What? What?
You're telling me you have 2 of them and you didn't know?
I can't believe it.
Back to back too.
Are you serious?
Yes.
I think I'm shook.
Cool.
Oh my gosh. How did I not know that?
That's actually a good question.
Really?
Yes.
Wow. Holy cow. learn something new every day. All right, well, many people believe that twins have a connection that is physical in addition to emotional. When studying twins, researchers analyzed this connection by notating the twins' headache patterns. First, each twin was randomly assigned a letter, A or B. Suppose that twin A has a 50% chance of getting a headache. If twin A gets a headache, twin B has a 30% chance of also getting a headache. If twin A does not have a headache, then twin B has a 10% chance of still getting a headache. We're going to draw a tree diagram to model this situation. So look, here's the deal, you guys. I've seen a lot of tree diagrams in my day. And people do this all the time, and they mess up this first level, right? Some people feel like this should be twin A gets a headache, and then twin B gets a headache. This needs to be about a single event, a single person or event occurring. And it's always going to be that the event occurs or it does not occur. So twin A gets a headache or they don't get a headache. So this is A headache or A no headache. Okay, so it's again, we're looking at a single event, and one of them is that it happens, the other is that it does not. Now, what is the probability that twin A gets a headache? 50%. So what's the probability that they don't get a headache? 50%. Okay, cool. Now, after twin A has a headache, we can now progress to the next event or the next person, and that is going to be after twin A gets a headache, then B might get a headache, or B does not get a headache. Same thing is true for A not getting a headache. Either B gets a headache, or B does not get a headache. So I have to look back at the problem to see what these probabilities are. If twin A gets a headache, twin B has a 30% chance of also getting a headache. That means that there's a 70% chance that they don't get a headache. If twin A does not get a headache, then there's a 10% chance that B is still going to get that headache. So there's a 90% chance that B would not get a headache. So there's a couple of sequences of events that could happen here. It could be that A gets a headache and B gets a headache. This would be the probability that A and B both get a headache. That would be 0.5 times 0.3, which is 0.15. So there's a 15% chance that both of these twins are going to get a headache. It could be that A gets a headache, but B does not. This would be the probability that A gets a headache and B does not get a headache. This is 0.15 times 0.7. 0.15 times 0.7. What is 0.15 times 0.7? 0.35. Now, in that situation, one of the two got a headache. It was twin A. Twin B did not. It could be that A does not get a headache, but B does. So this is A does not, but B does. This is 0.5 times 0.1. This is 0.05. A gets a headache, but B does not. And it could be that A does not get a headache and B does not get a headache. A does not and B does not. Neither of them are getting a headache. Everybody's happy. No headaches here. 0.45. The second part of this problem is slightly different than what maybe you've seen, but it is a probability distribution. We're going to let X be the number of twins that get a headache in the set of twins. Fill out the missing probabilities for neither twin getting a headache, so that would be 0, one of them getting a headache, or both of them getting a headache. So, what's the probability that neither of them get a headache? 0.45. That was this last probability we just found. What's the probability that one of them gets a headache? 0.4. How did you get 0.4?
You got the 0.35 and the 0.05.
Good. 0.35 and 0.05 get added together because in those situations, one of the two are getting a headache. All right, perfect. So that's 0.4. And then what's the probability that they both get a headache? 0.15. Perfect. Do you guys have any questions on that problem? That's slightly different than what maybe you've seen in the past. All good? All good. Awesome. Hey guys, what's the probability of A and B when they are mutually exclusive? 0. When you have mutually exclusive events, what can you do with their probabilities? And what do you get when you add those probabilities? The OR probability. When two things are independent, what can you do with their probabilities? Multiply. And what does that get you? The AND probability. All right, let's talk about student athletes and driving. One student from a high school will be selected at random. Let A be the event that the selected student is a student athlete. Let B be the event that the student drives. If A and B probability is 0.8 and the probability of B given A is 0.25, what is the probability that the selected student will be a student athlete? Hey, are these mutually exclusive? No, why not? They've got an 8% overlap. They are not mutually exclusive. It doesn't matter for this problem. I just am pointing it out. All right, you guys, there's a formula on the formula chart. It looks like this. Probability of B given A equals the probability of them both occurring divided by the probability of the given. That's on the formula chart. It would appear that we have been given 2 pieces of that 3-piece puzzle. So, the probability of B given A was 0.25. The probability of A and B was 0.08. And coincidentally, we are trying to find the probability of A, which is that the student is a student athlete. What a coinky-dink. Any idea how to do this problem?
Multiply 0.0.
Oh, so close. Algebra. So we need to multiply both sides by the probability of A. We got to clear out the fraction here. So the probability of A times 0.25 equals 0.08. So now I can divide both sides by 0.25. And that will give me the probability of A. 0.08 divided by 0.25, anybody? 0.32. Perfect. All right, students at a local elementary school were shown a painting and asked which emotion they felt by looking at the painting. The students were classified by their age. Here's their responses. One student from the school will be selected at random. What is the probability that the student is in the age group of 6 to 8 years old, given that they said joy? What's the probability that they're in the 6 to 8 year old group, given that they said joy? 28 over 89. You see that? Given that they selected joy. So joy is the condition, not the age group. Okay? Okay. Oh boy, Forrest Gump. You guys like Forrest Gump?
Yes.
All right, Forrest Gump, famous quote. Life is like a box of chocolates. You never know what you're going to get, right? All right, well, let's just see. Suppose a candy maker offers a special gump box that has 20 chocolate candies in it, and they all look the same. However, 14 of the candies have soft centers, and 6 of them have hard centers. And we're going to choose 2 at random. Construct a tree diagram for this sequence of events. We're going to let S be that it is a soft center and H be a hard center. I want to clarify here, guys. I'm not going back on what I told you guys on the twin problem. Soft and soft complement, but I'm just simplifying soft complement to be a hard candy. So this first event really is truly just a first event. It's soft and soft complement, also known as hard candy. Okay? All right, guys, what is the probability that your first selection is a soft-centered candy? 14 over 20. There are 14 soft-centered candies out of 20 candies in the box. What's the probability that the first one is a hard-centered candy? 6 out of 20. Now let me ask y'all a question. You get this first candy out of the box. What you gonna do with it? You're gonna eat it. It's gonna be gone. You're not gonna lick it and put it back. You're not gonna chew it and spit it out. You're not gonna swallow it and regurgitate it. It's gone. It's all gone. It's down in your stomach being eaten up by your acids. Okay? All right. Keep that in mind. What are you gonna do now? You're going back in for a second candy. That one was so good, you need another. So here we go. What might you get? Well, you might get a soft center. You might get a hard center. And that could occur after having either a soft or a hard center the first time. So let's see if you paid attention to what I just said. Let's assume you got a soft-centered candy the first time, and you are now digesting that one. What's the probability that the next one is soft-centered? 13 over 19. Because remember, one soft candy is in your belly. All right? So this is 13 out of 19. What's the probability that you get a hard candy after having a soft candy? 6 out of 19. Yes, good. 6 out of 19. Perfect. All right, let's assume that you got a hard candy first. What's the probability that you get a soft candy next? 14 out of 19. And if you got a hard candy the first time, what's the probability you get a hard candy the second time? 5 out of 19. Perfect. Good job, you guys. All right, guys, what is the probability that both of the candies have a hard center? This is the probability that the first is a hard center and the second one is a hard center. Basically, you got 2 hard centers in a row. Well, what was the probability that the first one was a hard center? 6 out of 20. What was the probability the second one was a hard center? 5 out of 19. So I take 6 out of 20 and multiply by 5 out of 19. This is going to be the probability. You got 2 hard candies in a row. I believe it is 0.0789. Aight. Here's the kicker. Given that the second candy was hard, what is the probability that the first one was also a hard candy? So we're asking here, what is the probability that the first candy was a hard center given that the second one was a hard center? The formula for this conditional probability is the probability that they are both occurring at the same time. So first and second are hard, which we already know that probability. We just found it in part B. But here's what we don't know yet. The probability that the hard candy was the second candy was a hard candy. We haven't calculated that probability yet. We're going to have to here in a second. So on the top, we do know what that is, 0.0789. But we need to deal with this whole situation here, this probability that the second candy was hard. How could it have happened? What could have been the sequence of events to get you a second hard candy? What sequence of events could have happened for you to have had a second candy that was hard?
It could have been soft or hard first.
It could have been soft and then a hard candy, or it could have been hard and hard candy. So it could have been either one of those. So I actually need, in order to find out the probability that they were both hard candies, I need to find both of those probabilities and add them up. Now, one of them we already know. The hard plus hard, or hard and hard, that was 0.0789. We already know that one. This other one, though, is 14 out of 20 times 6 out of 19. That's the probability that the first one was a soft candy and then you got a hard candy. And I believe that was 0.221. So the total of getting a hard second candy is the total of these two. So the probability of a hard second candy is 0.221 plus 0.0789, which is 0.2999, basically 0.3. 0.2999 goes here. Now I can take 0.0789 and divide by 0.2999. And what you get?
0.2631.
There's a 26% chance that if you got a second candy that was hard, there's a 26.3% chance that your first one was also hard. That is a very difficult problem. Please be careful when you're doing those kind of problems. Got it? Got it. All right, let's look at this last one on this page, and then we'll look at that other one first thing tomorrow. A high school science teacher has 78 students. Of those students, 35 are in band, 32 are on sports teams. 16 are not in band or on a sports team. One student from the 78 students will be selected at random. We're going to let B be the event that they're in band. S is that they're on a sports team. B and S are B and S mutually exclusive. Yes or no, and why. So we have band, no band, total. We have sports, no sports, total. And we're going to fill out this chart to see if band and sports overlap. So it tells us in the problem that we have 78 total students. 32 are in the band. 35. 35 are in the band. 32 are on the sports team. It also tells us that there are 16 that do not do either one. They're in band complement and sport complement. So, if there's 78 total and 35 of them are in band, how many are not in band? $43. All right. If there are 78 total and 32 of them are on sports teams, how many are not on sports teams? 46. If 46 of the students do not do sports and 16 of them also don't do band, how many of them don't do sports but they do band? 30. And the only one we care about is right here. Are there any kids that overlap between band and sports?
Yes.
How many?
5.
0.5. So are band and sports mutually exclusive? No, and the reason is that they overlap with 5 out of 78 kids.
That's neat.
In a standard deck of cards, there are 4 suits: hearts, diamonds, spades, and clubs. 2 of these suits are red, hearts and diamonds. The other 2 suits, spades and clubs, are black. Each suit has an ace, a king, a queen, a jack, and the numbers 2 through 10 for a total of 13 cards in each suit and a total of 52 cards in the deck. We are excluding jokers, so we're going to select a card at random. What's the probability that a card is red? So there's 2 suits that are red, hearts and diamonds. Each of those suits have 13 cards. So there are 26 cards that are red out of the 52 total cards. Okay, so that is half of the deck is red. All right, what is the probability? Oh, sorry, I should have written this down. Probability of red is that. All right, so what is the probability of an ace? So each of the suits has 1 ace, and there are 4 suits. So that is 4 aces out of 52 cards, and 4 out of 52 is 0.0769. All right, what is the probability that a card is red given it is an ace? So, given that it's an ace, we know for sure that it's an ace. That means that we know for sure that we have an ace in our hand, and there are 4 of those aces in our hand. All right, what's the chance that the card that we have is an ace and then it's also red? So there are 2 red aces, a hearts and a diamond. The ace of hearts and the ace of diamonds. So this would be 0.5. All right, what's the probability that the card is an ace given that it's red? So the number of red cards is 26. And so I know that I have for sure gotten a red card. Now, out of those red cards, what's the chance that it is an ace? So for red cards, there's hearts and diamonds. And each of those suits have an ace in them. So there are 2 aces out of these red cards. So 2 out of 26, which is 0.0769. All right, so let's look at these last couple here. And, all right, it says, based on your answers in part A through D, are the events red and ace mutually exclusive? So mutually exclusive means that they cannot happen at the same time. But as we saw up above, we can have a red ace. In fact, it happens twice. A red an ace of hearts, and an ace of diamonds. So since red and ace can occur simultaneously, they are not mutually exclusive. Okay, now, are the events red and ace independent? So, if the probability of red given ace equals the probability of a red, and the probability of an ace given red equals the probability of an ace, then they would be independent events. So let's just see if this is true. So the probability of red given ace, we found that in part C, that was 0.5. The probability of red, we found that in part A, that was also 0.5. So that one checks out. Let's check the other one. The probability of ace given red, that was 0.0769. And the probability of an ace was 0.0769. That also checks out. So red and ace are independent. What that means is if I know that I have a red card in my hand, it's not really going to help me very much with determining if I have an ace in my hand, and vice versa. That is 5.3.